Hello, I'm Andrew Logan and I'm going to go over a poster version of my paper which looks at the nature of the roots of the Riemann z function and the Riemann zeta function. I'll be giving links to the poster and to the longer paper at the end of the presentation along with my email address so you can get in touch with questions or comments. Starting with the problem. A key question unresolved in a Riemann's 1859 paper is the nature of the roots of the Riemann z function. Are they all real? Which is equivalent to asking if the roots of the Riemann zeta function, got a little graph of it here, see if their roots all have real parts equal to a half. To give an overview of the poster, first we'll look at an observation of the characteristics of the zeta function. We'll look at the Dirichlet eta function, which has the same zeros as the zeta function, but is proven to converge in the critical strip. Investigate the implicit functions where the real part of eta equals the imaginary part of eta, noting the regions where sigma and a are functions of each other. And we'll show that since the derivative of the real part of eta does not change sign when the real part of eta equals the imaginary part of eta, then the eta function only has a single zero on each separate curve. This is interesting. Combined with the property of the Riemann z function, z of s equals z of 1 minus s, this means that all the zeros have a real part equal to a half. We'll define s as equal to sigma plus ai for eta of s and zeta of s. The critical strip is defined as sigma greater than 0, less than 1. Riemann already proved that there were no zeros outside the critical strip, so we'll focus only on the critical strip. Firstly, that observation. We can see it in this graph here. What we've got in this graph are different curves with different values of sigma for the Riemann zeta function around a known zero. In this case, the first zero, just over 14. We can see here these arrowheads, this path here is showing the value of the real part of eta or the imaginary part of eta when real eta equals imaginary eta, and we can see here the nature of the curve. Always the derivative is always the same sign. Looking at that in more detail, going into something more formal so that we can show that that will always be the case. Firstly, the Dirichlet eta function. It's related to the zeta function by this expression here and is proven to be convergent uniformly but not absolutely for sigma greater than 0. So we can use it to explore the zeros of the zeta function in the critical strip. Looking at it in more detail, if s is a complex number, we can show the real component and the imaginary component of the zeta function. And looking at that in a little more detail, when the real part of eta equals the imaginary part of eta, then real minus imaginary equals 0, which is an implicit function that relates sigma and a when the real part of eta equals the imaginary part of eta. That function is shown in this graph here. And we can see here 2 points where you have effectively infinite derivatives for sigma, for d sigma dA and dA d sigma. This is important later on. The implicit function theorem, shown in the references, tells us that the above expression, being continuously differentiable, describes a curve with neighbourhoods where sigma is a function of a, except where d sigma dA is undefined, as the denominator is 0. Alternatively, where a is a function of sigma, where dA d sigma is undefined, where the denominator is 0. If we differentiate and rearrange, then we can find out what d sigma dA equals, and we can also see what the total derivative of the real part of eta is by substituting with the d sigma dA function multiplied by something else. You can do the same thing for dA d sigma as well, and you can also do the same thing for the imaginary part of eta, not just the real part of eta. Of course, given that we're saying that the real part of eta equals the imaginary part of eta, then the results, the values shown by those expressions will be the same. Looking at the next stage, it's useful to look at the harmonic addition theorem. This is a restatement of the way that you can add complex numbers. but it's a very useful way in this case for relating the real part of eta and the imaginary part of eta, despite the fact that they are infinite series of cosine and sine functions. We've got the definitions here. It's important to note here this beta definition. Beta is an amplitude, so it doesn't change sign as sigma and a are varied. Of course, that is if you don't rearrange the series, but can have a minimum of 0. It looks likely that it probably won't reach 0, but that we don't necessarily need to prove that for the purposes of this paper. If we apply this theorem to the derivative expressions above, substituting log 2 for omega naught, a for t, and noticing that the alpha I and phi I terms are identical for both the sine and cosine series, and noting that both the series in the expression for psi converge as they are phase-shifted versions of the sine and cosine series, and we can determine b from the value of psi and the convergent series of the real or imaginary component of eta, even though it may be difficult to show the convergence of the series for beta directly. What I'm saying is that this series here, it's difficult to show that it converges, but we can always determine what this is from the values that we can determine from convergent series anyway. Substituting those in, we end up with d sigma dA equals this expression, and the derivative of the total derivative of the real part of eta is a cosec function, beta times a cosec function. Similarly, dA d sigma is this series, and the total derivative of the eta function is a minus cosec function, which we can see is related to the one above, which of course you would expect. Important things to note now. Cosec's function has no zeros, so this total derivative has no zeros and is undefined in between sections of alternating all positive values and all negative values. These expressions are valid for all sigma and for value and a values for eta, and describe a single valued function for each sigma a input, except those points where d sigma a and dA d sigma are undefined. Expression 1 describes the number of curves with neighbourhoods where sigma is a function of a, except where expression 1 is undefined when the denominator is 0. Expression 2 gives the derivative of the function which describes the value of the real part of eta in those neighbourhoods, which is positive in one neighbourhood where sigma is a function of a, i.e. the value of the real part of eta increases for increasing a. I've got the opposite case in brackets, of course. Increasing a is undefined at the same points where expression 1 is undefined, and is negative, similarly positive, in the adjacent neighbourhood, i.e. the value of the real part of eta increases for decreasing a. What that means, if we relate that to this graph here, that would mean if there is no undefined area, you have this shape graph. If it does go undefined, so you end up with an infinite derivative, say for instance this curve bends back here, what it's saying is that this will still continue to increase even as a decreases, basically saying that value of that expression will keep going up. It won't come back down again. This means that each separate curve segment describing the value of the real part of eta where real eta equals imaginary eta always has a positive, or if it starts out negative it will continue negative, if it starts out positive it will continue positive. Same argument holds for expressions 3 and 4. When you say all positive, that does not exclude 0. 0 can have the sign positive or can have the sign negative. The main point is that it doesn't change sign. This means that the separate curve segments described by expression 2 and expression 4 either have all positive or all negative derivatives, not changing sign, although individual segments might have positive or negative derivatives, which means that they can only have one 0 per curve. This in turn means that there can only be a single zero in the local region of any particular value of A. Now, combining that with one of the key properties of the Riemann z function, which has the same zeros as zeta and eta, and has the property that z of s equals z of 1 minus s, this means that for each value of A there is at most one zero. We've shown that here, and because of the z of s equals z of 1 minus s, that zero must be at sigma equals a half for zeta of s and eta of s, which means a real zero in the case of z of s, which is the conclusion of the Riemann hypothesis. It's proved. Here's a review of the conclusions, and here are the links to the poster, the paper, and my contact details. Thank you.